So, welcome back to the class on electronics testing. So, yesterday we talked about logic based, we talked about how we can use what are called as bilbos. Built-in logic block observers. So, one of the exercises I had given you was to build a bilbo, right. So, let me illustrate that today. Before that, let me recall that there were two types of LFSRs that we talked about, right. One of them was called Fibonacci and the other was called Galois. So, the Galois LFSRs can be derived from Fibonacci LFSRs. So, let me explain that. So, remember, yes, we talked about this LFSR, right, the polynomial, LFSR polynomial we had considered was 1 plus x power 4 plus x power 5 plus x power 6 plus x power 8. And if we want to write the Fibonacci one, this is how we had done it. We had created a shift register. So, there are 8 flops in this example because the LFSR polynomial is of order 8, and I will not write the clock, etc., right. So, this is a shift register. If you remember, we label these as 1x, x square, x cube, x power 4, x power 5, x power 6, x power 7 and x power 8. And recall that the taps we are looking at are x power 4, x power 5, x power 6 and x power 8. And we build either a 4-bit XOR, or we can also build something like this. And we connect it back to this. So, essentially it is a XOR of x power 4, x power 5, x power 6, x power 8. Okay. So, this is what is the Fibonacci LFSR polynomial for this. So, if you want, you can label these as 0, 1, 2, etc. I believe yesterday we illustrated this using the Excel sheet, right, how this. The problem with this guy is you need an XOR tree. Okay. So, this is and also it is not a regular layout. So, not a regular layout. In comparison, the Galois polynomial is much better. So, what we will do is, see, we see x power 4, right. So, write 4 flip flops, okay. Then write another one and another one, right. So, the first XOR gate will occur here. So 1, 2, 3, 4, that is the first x bar 4 that you see here. Okay. And then the next one will be here. And then x bar 6, so one more. So, to the left of the first XOR gate we will have 4 delays, to the left of the second one we will have 5 delays, and to the left of the third one we will have 6 delays. Okay. So, we will label these as 0, actually here it will be better to label them 7, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And the flip flop, the feedback comes from here. Okay. So, this is the Galois LFSR. No XOR tree, okay. It requires 2 input XOR gates, and you can actually build a cell like that. And then the layout will be very regular, right. So, let us do this simulation also like yesterday and establish that this also works. So, let us write down 8 columns, okay. In the first row we will enter the the names of these signals, right. So, I had labeled them 7, 6, 5, etc. So, I will call them x7, x6, x5, x4, x3, x2, x1, x0. We will start by a seed. So, the seed could be any 8-bit pattern, but we will start with 0, 0, 0, 0, then 0, 0, 0, 1. So, we will start with this as the seed. And so, remember the first XOR occurs after 4 delays. So, here is the first XOR. So, we will have to write XOR of D2 and H2. Okay. So, the feedback is coming from H2 and the neighbor D2, right. And in order to avoid this true false etc., we can add this plus 0. Okay. The next one also has an XOR gate. Okay. So, that will be XOR of E2 and H2 plus 0. And the third one has XOR of F2 and H2 plus 0. Okay. So, let me just show you here. So, we have these 3 XOR gates. Okay. So, after the 4th flip flop an XOR gate, after the 5th one there is one, and 6th one there is, and this guy feeds back here. So, we will have to this is simply equal to G2, okay, and this guy is simply equal to H2, and this will be equal to A2 because we are just shifting in, and then this is B2, and this is D2. Okay. So, let us write down the decimal equivalent of these bits, right. So, this is a state of the LFSR. So, this is equal to x7 multiplied by 128. Okay. I am sorry, not x7, A2 times 128, because we are looking at this as a binary number 00000001. So, the weight of A2 is 128, the weight of B2 is 64, the weight of C2 is 32, the weight of D2 is 16, the weight of E2 is 8, the weight of F2 is 4, the weight of G2 is 2, and last but not the least H2 is 1. And if you drag this, you will see the next one will be 142. So, it has gone to state 142. Now, if you pull this down a little bit, you will see, just a minute. So, and we can continue to generate the next state. Okay. So, we just simulated an 8-bit Galois LFSR. So, we started with 0001, that is row number 2. So, 255 clock cycles later, that is row number 257, you can see that it repeats again. Okay. Then 142, 71, the same sequence will repeat. Okay. So, all the 2 to the power 8 minus 1 states were generated. Okay. We will verify that nothing is repeated. Let us look at 142. Okay. And you have to use this, this one you should say look only in the values. Okay. You can see 142 occurs here, and then 142 occurs at 258. Okay. There is no repetition of 142. Okay. So, similarly you can look at 71 or something like that. So, it occurs here and then occurs here. So, at line number 4 or the row number 4 it occurs, then row number 259 it occurs. Okay. Let us look at 255. Okay. So, 255 occurred at line number 82, then again I think we have not yet generated that. So, we have to generate it. The second iteration of 255 has not happened yet. So, we need to extend it a little bit more. So, we have simulated it for almost 600 cycles. So, the first occurrence of 255 just a minute. Let us go back. So, the first occurrence of 255 occurs so one it occurs at line number 82, I believe, right. Then the next one will occur at 82 plus 255. Oh, we have not computed this, sorry, my mistake. Okay. So, again let us try doing this. So, so you can see it occurs at 337. Okay. So, 337 is okay, then the next one will occur at 82. 82 and by labeling these guys. Okay, this is let us say 1 cycle number 1, 2, 3, etc. And let me just extend this, that may make this easy. So, now let me sort these guys on the state value. So, that will clearly bring out so data sort sort by column J, okay, and let us say smallest to largest. See, now it makes sense, right? State 1 occurs, let me also sort this on K, right. Sort, so first on J and next on K. So, now it makes sense, right. No, so not right. Just a minute. So, we started with 00001, then when does the first one come again? When does 1 come again? It should happen at 256, right. See, it does happen, okay. I do not know why, okay, this state is wrong. So, why is it showing 911 here? It should have shown the number there, that is 256 it should show. That is a mistake. See, we should not have 411 here, it should have 1, 2, 3, 4, etc. Okay, now let us try. Now copy all of this. Create a new sheet, copy everything, only the values. And then sort on state, then followed by 11, the cycle. See, now it looks correct. So, 1 occurred as state 1, then 256, 511. So, they are all separated by 255. Similarly, 2, okay, it occurred at 255, then 510, 6, 765, etc. Yeah. Right. So, it is working correctly as a Galois LFSR. Okay, I hope everybody understood this. Right. So, let me illustrate this one more time. Maybe I will do it for the 3-bit LFSR. So, if you recall, this was our Fibonacci LFSR. So, we used to call this 0, 1 and 2, and this is x square and x cube. So, 1 plus x square plus x cube. We already know how this works, right. So, if you have initialized it to 0, 0, 1, then the XOR of 0 and 1 will appear here, and these two will shift. XOR of these two will appear 0, and these two will shift. Then 1, 0, 1, 1, 1, 0, then 1, 1, 1, 0, 1, 1, then 0, 0, 1. Okay. So, this is the first cycle, second, third, fourth, fifth, sixth, seventh, eighth. So, one repeat after. So, everything will repeat after this. Now, let us form the same thing using Galois. Okay. How do I do that? The first one should have 2 flip-flops ahead of it, then an XOR gate, and then this. Okay. Only one XOR gate will be there. This guy will go back here, and this will feed here. So, the state, suppose I initialize it to 0, 0, 1. Then in the next clock cycle 1 will come here, and the XOR of this and this will come here, and this 0 will come here. In the next clock cycle this 1 will come here, the XOR of these two will come here, and this 1 will come here. In the next one, this 1 will come here, the XOR of these two will come here, and this guy will come here. This 0 will come here, the XOR of 1 and 0 will come here, and this 1 will come here. And then 1 will come here, XOR of 1 and 1 will come here, and this 0 will come here. Then this 0 will come here, then XOR of these two will come here and this one will come here. And then this 0 will come here, XOR of these two will come here and this 0 will come here. So, it has cycled back to the same state. Once again this is happening 1, 2, 3, 4, 5, 6, 7, 8. So, it has 7 unique states. Okay. So, you can see all the states got generated 1, 2, 3, 4, 5, 6, 7. Okay. So, all the states got generated in both of the order in which they got generated is slightly different. Okay. So, this is what you have to understand.